Lesson 2, solving equations using numerical methods, iteration. So in today's lesson, we're going to introduce a concept known as iteration, which can be used to find approximate answers to equations which we may not be able to solve algebraically. Before we actually go into the method and the procedure, we need to introduce a little bit of notation so you understand exactly what the different formulae mean and how they work. So we're going to start off by introducing something called suffix notation. Now, what is suffix notation? Let's have a look at some examples. So let's consider a sequence of numbers. My sequence of numbers is going to be 5, 7, 9, 11, 13, so on, like that. It's a very, very simple sequence, and you can probably see how we would move from term to generate each new term from the previous one. So you can see we add 2 each time to generate the next term. Now, we can label the terms very, very neatly using what we call suffix notation. So term 1, I would label it as T with a little suffix here of 1. So that's the suffix, the number at the bottom, the small number here. That's all it is. And it just indicates that we're talking about term 1. So term 1 is equal to 5. What about term 2? I would write it as T2, which is equal to 7. T3, which is 9. T4, which is 11. T5, which is 13. And so on. And we could generate more terms if we wanted to. Now, what's nice here is that we could actually write down a formula that allows us to jump from one term to the next term. So I could say that the next term is equal to the previous term plus 2. That makes sense, doesn't it? For instance, here, 13 is equal to 11, the previous term, plus 2. So I could say term 2 is equal to term 1 plus 2. That makes sense, doesn't it? Term 2, which is 7, is equal to term 1, which is 5, plus 2. I could say that term 3 is equal to term 2 plus 2. Term 4 is equal to term 3 plus 2, and so on. But what I would like to do is aim to generalise this and write down a more general formula than this. So let's say that a particular term we are talking about is term n. Now, how would I then write the term that comes after it? Well, the suffix would have to be one more than the current term. Have a look at this. If the current term is T3, the next term after it would be T4. So if our current term is Tn, what's the term after it? It's one more than n, it's Tn plus 1. So the suffix is Tn plus 1. And for this particular sequence here, I generate the next term by taking the previous term and adding 2 to it. And this result here is something we call an iteration formula. Now, what does iteration actually mean? Iteration simply, in this particular context, just means we repeat something and we generate more and more terms. So when we create our sequence, so we stopped at term 5 previously, term 6 is equal to 15, term 7 is equal to 17, so on. As I generate more terms, I'm using the iteration formula here to iterate and create more terms. So iteration just means this process of applying a formula in a repeated fashion which just generates more and more terms. So let's take a look at another example. Again, I'm going to write down a sequence to begin with. So we have 15, 11, 7, 3. Can you write down the next number in the sequence and write down the pattern that takes you from term to term as you generate new terms in the sequence? So hopefully you spotted that each time you generate a new term, you subtract 4 from the previous term, which of course means that the next term will be 3 take away 4, which gives you -1 as the next term. So let's now write out our terms using our suffix notation again. Term 1 is equal to 15, term 2 is equal to 11, term 3 is equal to 7, term 4, 3, term 5, -1. So if we try and write this out as an iteration formula again, we can see that the next term is equal to the previous term, or the one before it, subtract 4. So for instance, T5 is equal to T4 take away 4. We can see that looking at the numbers over here. So again, let's generalize this. What about if we pick a particular term and call it Tn? Again, the term that comes after it will be Tn plus 1, and Tn plus 1, the next term, will equal the previous term, take away 4. So again, here is my iteration formula. So in this next example, I'm going to write out the terms of the sequence using suffix notation, and I'd like you to see if you can spot the pattern that connects the terms. Can you write down what you think T5 is going to be? So hopefully you've seen that each time we generate a new term, we multiply the previous term by 2. So term 5 would be equal to 24 multiplied by 2, which gives us a value of 48. So from here, can you now write down the iteration formula Tn plus 1 in terms of the previous term Tn? So again, you may want to do this in words before you use algebra. So we could say the next term is equal to the previous term multiplied by 2. So Tn plus 1, which is the next term, is the previous term, Tn, multiplied by 2. But rather than writing times by 2, we'll write 2 lots of Tn like that, which is a neater piece of algebra. So again, here's our iteration formula. Now, have a look at the terms in this fourth example, 2, 12, 62 and 312. Can you see the pattern here, how we're jumping from term to term? It's a little bit more complex than the previous examples. So you may have worked out that we multiply by 5 and then we add 2. Multiply by 5, add 2. Multiply 62 by 5, and we get 310, add the 2, and we get to 312. Now, we're going to use suffix notation again to list our terms here, but we don't have to use the letter T necessarily. We can use any letter we want to. T, I suppose, sounds like it refers to term, so it's a good letter to use, but I could say U1 equals 2, U2 equals 12, U3 equals 62, U4 equals 312. Can you now see if you can write out the iteration formula here? So the next term, which is un plus 1, is 5 times the previous term, which we call un, add 2. And it's really important that the add 2 is a clear, large add 2, which is not part of the suffix. The suffix is just the un part here. So here is our iteration formula written in terms of u. Now, as a formula, it's not very useful if you want to find a specific term in the sequence. For instance, I can't use this formula very easily to find the 29th term. To do that, I would have to work out the first 28 terms and then get to the 29th term. But it is useful if you want to generate term after term after term, and we will see how this links in with solving equations a little bit later on. So, having looked at iteration formulae, let's see if we can actually use them to generate sequences. Let's take a look at the first example here. Tn plus 1 equals 3Tn plus 5. I always think it's useful to actually make sure we understand exactly what this formula is saying. And this one is saying that the next term in a sequence is 3 multiplied by the previous term, add 5. So you know exactly what's happening. So let's generate a few terms manually. T1 equals 2. T2, the next term, is 3 times the previous term of T1 plus 5. So that's 3 multiplied by 2 plus 5, which is equal to 11. Can you work out T3? It's 3 times the previous term of 11, 33, plus 5, which gives us 38, and so on, and we can keep generating terms. Now, that takes a long time if you're going to do this manually, and if you're going to type in every calculation into your calculator, it can also take a long time as well. So what we're going to look at is a nice shortcut that you can use on your calculator to generate an iterated sequence of terms using an iteration formula. So here's what you need to input on your calculator. Start by entering term 1, which is 2. Now, press the equals sign. Now, this stores the first number that you've entered, which is 2, and it becomes the answer. So what we're now going to do is use the answer key to set up the iteration formula. So I would then, for this particular iteration formula, input 3 multiplied by the answer, and you can see the answer key on your calculator, plus 5. Once you've done that, press the equals button again. Now your screen should say 11, which of course is the next term. Now, all you have to do to generate the next term and the terms after that is to keep pressing the equals button. So press the equals button again once and you should find you get term 3, which is 38. Now the beauty of this is that you can keep generating new terms by simply pressing the equals sign. You don't have to input the formula in again because you did that at this stage here and you set it up as an iteration by using the answer key on your calculator. Now this will be fantastic a little bit later on when we come to solve equations using the process of iteration. Now let's have a look at this second example. We have another iteration formula, un plus 1 equals 2un squared minus 3. So just to be clear, you are squaring the previous term and then multiplying by 2 afterwards. So again, I'm going to write out what this means in words. It's telling us that the next term is equal to 2 multiplied by the previous term squared and then subtract 3. So square the previous term, multiply by 2 and then subtract 3. That's the order in which we need to work. So u1 is equal to 3. u2 would be equal to 2 multiplied by 3 squared, take away 3. Let's work that out. That's 2 multiplied by 9, take away 3. So 18 take away 3 or 15. What about u3? Well, u3 would be equal to 2 multiplied by 15 squared, take away 3. Let's work that out. It's 447. But what would be good is to see if we can now generate this on our calculator. So use our calculator to perform the iterations. So you need to follow all of the steps that we set up previously, except this time when it comes to the blue step over here, you need to make sure you enter the correct iteration formula for this particular question, which means you need to input 2 multiplied by answer squared. And of course you've got the squared button, which looks like this on most calculators, x squared, and then subtract 3. So 2 multiplied by answer squared and then subtract 3. So that's the iteration formula that you're going to set up on your calculator. Of course, don't forget to enter the first term first of all, which of course is 3. So follow these instructions carefully and see if you can generate the terms of the sequence. So you're going to see a short video demonstrating these steps that we've just seen on the calculator. It is a slightly different make of calculator to the one that you use, but the principles are exactly the same. So let's have a look at this. We start off by inputting 2, the first value. We press equals. We then type in the iteration formula, 3 times the answer plus 5. Press equals, we get term 2, which is 11, and then keep pressing the equals sign, you get term 3, and so on and so forth. Now we approach the big question. How does any of this relate to the concept of solving an equation? So to answer this question, we need to think about an equation, and I'm going to give an example that we can use. So let's suppose we're asked to solve the equation x squared plus 3x equals 50. Now, hopefully you recognise that this is a quadratic equation. So to solve it, we need to ensure that one side is equal to 0. So subtract 50 from both sides, and we end up with x squared plus 3x minus 50 equals 0. Now, you can try, but you won't be able to factorise this equation, so we're going to need to solve it using the quadratic formula. So the big question is, do we remember our quadratic formula? Let's see if we can write it down. Again, you might want to pause, see if you can write it down from memory, and then check your answer. X is equal to minus b plus or minus the square root b squared minus 4 multiplied by a multiplied by c, all divided by 2a. So let's go back to our quadratic equation over here, and let's make sure we write down our key values. So a, first of all, we have 1x squared, so a is equal to 1. B, remember, is our coefficient of the x term, so b equals 3. And as I always advise, write down the value of b squared as well. It's equal to 9 in this case. And c is our constant term at the end. C is equal to negative 50. So x is equal to, and let's start substituting in our information. So minus b is negative 3 plus or minus square root of b squared, which is 9, minus 4 multiplied by a, which is 1, multiplied by c, negative 50. Close that bracket. All divided by 2a, which will just be equal to 2. So let's simplify the part underneath the square root sign. So we have negative 3 plus or minus the square root of 209 all over 2, and let's write down the two answers that we get as a result of this. So remember, we're going to have x equals minus 3 plus root 209 all over 2, and our secondary answer will be x equals minus 3 minus root 209 all over 2. So let's write down and round both the answers that we get. So here they are. We have 5.728 ... which I'm going to round to 5.73 to 3 significant figures, and my secondary answer, negative 8.728, which will round to negative 8.73 to 3 significant figures. Now, you may be wondering why we've suddenly segued into using the quadratic formula, but I promise this will be important a little bit later on. So here's what I want you to take away from this, and here is what I want you to really make sure you remember from what we have just done. I want you to remember this was the equation here that we were solving, x squared plus 3x equals 50, and I want you to remember that we found these answers, 5.73 and negative 8.73. So make a really careful note of this because this will come up again. So we're now going to try and tie everything together and find out how iteration formulae have anything to do with solving equations. So I want you to look at this example of an iteration formula here. xn plus 1 is equal to the square root of 50 take away 3 times xn. So remember, this gives us the next term, and to generate it, we take the previous term, we multiply it by 3, we subtract that from 50, and then we take the square root. So to start, we make sure that we have a starting term, which you need to be told. So I'm going to tell you that x1 here is going to equal 2. Now, x2, we can then generate using the calculator. So remember how you do this on the calculator. We looked at this on the previous slide. Remind yourself if you need to do this. Input your first term, press the equals key, and then you need to input this iteration formula using the answer key to replace xn. So you would have something on your screen that looks like this, 50 take away 3 multiplied by answer, and you use the answer key there to input answer. Press the equals button again and you will generate the second term in this sequence. Now what is that second term? It's x2 and it is equal to 6.6332 ... Press the equals button again and you'll generate the third term in the sequence, x3, 5.4863. What's x4? It's equal to 5.7914 ... And I want you to keep generating terms, keep going. Now, what you will notice is that as you generate more and more terms, the numbers change less and less, and the terms in the sequence start to become very, very similar. Now, this is a process known as convergence. We say that the terms in the sequence are converging to a particular value, and you will notice that that value is approximately 5.7284. Now, over here on the right-hand side, you can see I've used a spreadsheet to generate more terms of the sequence. We go up to x17 here. Look at the values. Can you see the convergence? Can you see that they are all converging to a value that looks to be around about 5.728? Now, if we carry on going, there will come a point where Excel cannot actually show the changes any further because it will only be accurate up to a certain number of decimal places. So the terms will start to look identical. And even though there might be small changes further along the number, we can't actually see them on Excel. So where have we seen this number here before? 5.728. Well, you saw it a minute ago when you solved the quadratic equation x squared plus 3x minus 50 equals 0, because you found that one of the answers to that was 5.728 ... which we rounded to 5.73 to 3 significant figures. So in answer to this question, what is this sequence converging to? Well, this sequence appears to be converging to one of the roots of this quadratic equation. Now, this leads us on to some other questions here. Can we find the other root? Because if you remember, the quadratic equation here had two roots. One of them was x equals 5.728 ... but there was another root which was x equals negative 8.728 ... So is it possible for us to find this answer to our quadratic equation as well? And my third question is, where did this iteration formula come from? So where did this magic formula come from that allowed us to solve this quadratic equation? Now, just by looking at the original quadratic equation in green and the iteration formula up at the top in white, you can see there's a connection here. We can see the 50, we can see the 3, we can see the x's, squaring, square rooting. There are some definite connections there, but we need to explore this in more detail. So in a minute, we're going to answer the questions in this order. We're going to see where this iteration formula came from, and we're going to see whether it's possible to use it to find the other root. So, where did this iteration formula actually come from? Let's start by discussing this. So, the original equation, the quadratic equation which we solved using the quadratic formula, was, in its starting format, x squared plus 3x equals 50. Now, here's what I'm going to do with this. I'm going to start off by subtracting 3x from both sides. Now, this gives me x squared equals 50 minus 3x. And I'm then going to square root both sides, so x is equal to the square root of 50 minus 3x. Now, you may be thinking, well, that's a very unusual way of rearranging a formula. Normally when we do that, we don't like to have x on both sides of the equal sign, but look at the structure of it. X is equal to the square root of 50 take away 3x. There's the basis of our iteration formula. And what I'm going to do is take this x here and rewrite it as xn plus 1 equals the square root of 50 take away 3. And then this x over here, I'm going to write it as xn. So here is our iteration formula. And it was created by rearranging the original equation that we had to solve into a format with x on both sides. One x then becomes the new x, or the new term, xn plus 1, and the other x, or there might be multiple x's on one side, become xn, or the previous term. So let's have a look at our iteration formula in a little bit more detail. Now, previously when we used it, we started with x1 equal to 2, and we found that using the iteration formula created a sequence of convergent terms which gave us an approximate answer to our quadratic equation of about 5.728. Now, what happens when we start with different starting points? So have a look at the second example here, where x1 is equal to 5. Now, you will notice that the sequence once again converges to that value of about 5.73 very quickly. What happens if we start with x1 as a negative number, negative 7? Well, again, you'll find you get convergence to that root of 5.73. So, is it possible to generate this root with any starting point? Well, have a look at what happens if we start with x1 equals 20, and you'll see that things go badly wrong very, very quickly. Excel does not like this at all. Now, why is that? It's because x2 is the square root of 50 take away 3 lots of x1. Well, 3 times 20 is 60, so this then gives you x2 is the square root of negative 10, and you can't compute this. So the system breaks down. So it's not always possible to use any particular starting value that you want to. If you can choose a starting value that's closer to the root, then that will allow you usually to get to your root much more quickly, and you can see that with the second example where we start with x1 is equal to 5. But even starting with -7 or 2 gets us to 5.728 very, very quickly. Now, have an experiment with this yourself, try different starting values. Can you get to that other root, which was about -8.72? 8 dot dot dot. What you will find is, regardless of which starting value you use, you cannot get to that particular root with this iteration formula. So that's really important. Not every iteration formula will allow you to find every root. And that's because it's possible to create more than one iteration formula. Now, let's have a look at this iteration formula. Remember, quadratic equations have two roots, and the quadratic formula involves a plus or minus. So at the point at which I square rooted both sides in my rearrangement, what if I had taken the negative root instead? So what I'd like to do is now use this as your iteration formula. Let's take x1 as 2 again, and then input this into your calculator and see what happens. Well, here we go. You can see what's happened with the Excel spreadsheet when I've done this. We start with x1 equals 2. We make use of this new tweaked iteration formula, and you will see that the terms converge to the other root of -8.72. So it may be the case that if an equation has more than one root, for instance, quadratic equations will have up to 2 roots, you may need to use different iteration formulae to find different roots, and you may need to potentially choose your starting value, your x1 value, very carefully in order to ensure that your sequence converges to your root. So we're going to look at using iteration to find the root of a different equation. First job, we need to find an iteration formula. Now, there are many different ways of rearranging to find different iteration formulae, and you will explore that yourself a little bit later on. For the moment, I'm going to pick a particular strategy, follow the algebra, make sure that you can understand exactly what I am doing here. So firstly, I'm going to add 5x to both sides. So I end up with x cubed plus 2 equals 5x, and I might just write it out the other way round, so 5x equals x cubed plus 2, and then I'm going to divide by 5, so I've got x is equal to x cubed plus 2 over 5. So look at my rearrangement. I've rearranged to the form x equals, but x has to be on both sides as well, because we're going to convert this to our iteration formula. So we have xn plus 1 equals xn cubed plus 2 all divided by 5. So here's our iteration formula. Now we're going to choose a starting value. Again, I'm going to tell you the starting value. So this is equal to x1, which is going to be 1. Now we have to be a bit more careful now, because we have to find a root that's correct to 2 decimal places. So how do we know how many values of x to generate? In theory, if we use a spreadsheet, we can generate several values very quickly, and then it's very easy to see what the answer is correct to 2 decimal places. This is quite a low degree of accuracy in comparison to what a spreadsheet can do. Now, for the purposes of GCSE, you are allowed to stop when 2 consecutive values that you generate are equal to 2 decimal places, or the degree of accuracy to which you are rounding. Those of you who go on to study A-level maths will learn much more about this, and actually there are a few more steps that really need to be considered, but for the purposes of GCSE, we can use this basic rule. Now, the best way to set up our working is to make sure we have a table of values. On the left-hand side, we're going to write down at least 5 or 6 decimal places of accuracy for each iteration, for each value we generate. And then on the right-hand side, we're going to write down the value rounded to this degree of accuracy for this question, which is 2 decimal places. So x1 is equal to 1. There's no rounding really to be done there. Make sure you set this up on your calculator using the answer key here to generate subsequent values of x. So x2 is equal to 0.6. Again, there's not much rounding to be done here, 1 and 0.6. What about x3? It's equal to 0.4432. So to 2 decimal places, that's 0.44. So we don't have any form of agreement yet between two consecutive values. Let's generate x4. This is equal to 0.41741. So notice I'm writing down at least 5 decimal places of accuracy here. I'm not going straight to 2 decimal places. I'm showing my working clearly. So this gives me 0.42 to 2 decimal places. Remember, that's our degree of accuracy for the question. x5 is then equal to 0.41454 So that is 0.41 to 2 decimal places. So check your rounding really carefully in each example. Let's generate another x value. x6 is equal to 0.414247 So rounding this to 2 decimal places gives me 0.41. So for the purposes of GCSE, I can now stop and I can say that my answer is going to be x equals 0.41, correct to 2 decimal places. So let's look at another example. We're given the equation 2x squared plus 2x minus 3 equals 0, and we need to rearrange this to generate this iteration formula here. So we need to isolate x on one side, and there will still be x terms on the other side. I notice that there's no square rooting going on in this result over here, which gives me a little bit of a hint as to how this might work, and there's a lone 3 on the right hand side. So I'm going to start off by adding 3 to both sides, which gives me 2x squared plus 2x equals 3. I'm then going to factorise on the left hand side, so I've got 2x, x plus 1 equals 3, and then I'm going to divide both sides by 2, and I'm going to divide by x plus 1. This then leaves me with x on the left-hand side, and on the right-hand side I have 3 over 2 bracket x plus 1. And there we've got the structure. We just need to replace x with xn plus 1 on the left-hand side, and then on the right-hand side we're going to replace the x with xn. And here's the iteration formula. Now, we're going to use this iteration formula to generate a root of the original equation correct to 2 decimal places. So remember, we need a starting value, and we're going to choose x1 equal to 1. Don't worry too much about choosing a starting value. If you choose something and you feel that it's not converging, you're not getting a neat convergent sequence of terms, you can always start again and choose a different starting value. Exam questions will tend to guide you as to which value to select. So we're going to set up a second column which looks at rounding all of the values to 2 decimal places. The first one doesn't require much rounding. So set up your calculator to iterate using the answer key and write down the values that you get and round them. You can either work through with the video or pause, work it out yourself, and then check your answers. So x2 works out to be 0.75. So that doesn't require rounding to 2 decimal places. x3 is 0.85714, which rounds to 0.86 to 2 decimal places. x4 is 0.80769, so 0.81 to 2 decimal places. x5, 0.82978, So 0.83 to 2dp. X6 is 0.81976 rounded, which gives us 0.82. And then X7 is 0.82428, which is 0.82 to 2 decimal places. So at this point, we have two values which agree to 2 decimal places, two consecutive values which agree to 2 decimal places. So I'm going to say that my answer is X is 0.82 to 2 decimal places. So here's your chance to explore. You're going to consider the equation x squared minus 4x minus 7 equals 0. You're going to use rearrangement to find about 5 different iteration formulae and test these out. You can choose your starting values of x. Do all your formulae work? Can you find both roots of the equation using one or more of your formulae? Now, how will you know if you're getting 2 answers? Well, your sequence of terms should converge if that's happening, and you can always check whether you're getting the correct values by using the quadratic formula to check what the actual answers of x squared minus 4x minus 7 equals 0 are. So just to give you an idea, here are some of the different iteration formulae that you may have found. So you can see I've listed 5 different iteration formulae that we could try out. Now, choose some different starting values, see whether they converge to give you either of the roots. So, what did you find out? Well, you should have found out that this one does actually converge, and it gives you x equals 5.32 to 2 decimal places. Now, this one, interestingly, doesn't work. You get to a point where after x2, because x2 is negative, you then end up trying to square root a negative number, so it's not possible to actually continue the iteration. This one converges as well and actually gives you the other root, x equals negative 1.32 to 2 decimal places. This one also converges, taking you to x equals 5.32. And this one also converges, taking you to x equals negative 1.32. Now, I used x equals 1 as a starting point for every one of my attempts. You might find that something different happens if you have a different starting point. Very interesting to explore and see what happens. Do you get any divergent sequences? That's where the terms start to get further and further apart and do not converge to a particular root.